Bonjour tout le monde. Donc, ça fait plaisir aujourd'hui d'accueillir une de mes principales collaboratrices. J'ai vérifié ce matin sur ADS. Depuis 2015, on a 20 articles ensemble, tous les deux. Donc, on travaille tous les deux ensemble. Donc, Siyi a complété son doctorat à UCLA en 2014 sous la supervision de Mike Dwarfs sur l'étude des planétésimals autour des étoiles blanches. Et ensuite, elle est allée faire un postdoc à l'ITESO en Allemagne, suivi d'un travail de fellow astronomer au Cerveau Montréal et le PLD au Chili. Et depuis 2017, elle est instrument scientist associate astronomer à Gemini Observatory. Et elle s'intéresse à la poussière, aux disques et aux gaz circumstellaires autour des étoiles blanches, à la composition chimique des planétésimaux et aux planètes en transit autour des blanches. Donc, c'est de ça dont elle va nous parler aujourd'hui. Donc, sans plus tarder, je vais lui laisser la parole.
Thank you. I didn't realize it would be in French. Okay, all right. Okay. Hello. Good morning, everybody. Yeah. So my name is Siyi. I am an astronomer at Gemini Observatory and NSF NOAA. Very glad to be here and have a chance to tell you about my research. So my topic is planetary systems around white dwarfs. So I just want to say, if you have any questions, please feel free to interrupt and ask. I love feedback. And I also want to say, I am an observer. So, and then I collaborate with the White Dwarf group quite a lot here. And so my perspective on this will be more geared towards observation. And maybe another thing, just fun fact, last time I was in Montreal, it's about 10 years ago, I was here for the European White Dwarf workshop, which is kind of funny because when I was applying for my Canadian visa, they asked, why do you come to Canada? And I said, I'm here for the European White Dwarf workshop. so just say, yeah, I'm on sabbatical. So I'm currently based in Boston. And so Montreal is such a short hop, right? So I'm like very happy and very glad to be here. And the weather has been great. I'm from Hawaii. I almost want to complain it's too hot. Okay. All right. So with that, let's get started. Okay, maybe first a little bit about Gemini Observatory, about where I'm from. Gemini, we were named after the constellation. So the idea is we are really a twin telescope. So we have one, like this is one in Chile, because you can see the large and the small Magellanic Cloud almost, and that one is in Hawaii. So we are like twins, so we are almost the exact copy, but not quite the same. So for the theorists in the room, you might wonder, why do we need two telescopes? Any thoughts? Why do we need two? Sure, two. Yeah.
Hemispheres?
Yes, exactly. Yes. We look at different parts of the sky, and two is better than one, right? So anyway, so we have two telescopes, and I really enjoy working in an observatory. And so I work there, which is like Hawaii. And then that's the island with active lava, right? So that's kind of what's happening in June. And then it stopped a little bit, and then it erupted again. So it's the third time it erupted this year. So that's Kilauea, the most active volcano on Earth. So Hawaii is a very unique place. So if you ever come by, let me know. I'll be happy to show you around and the observatory. All right, know enough about me. Let's get to the science. So, and I want to start with the solar system today. So this is kind of a cartoon image of the solar system. There's quite a lot of things happening, and we have terrestrial planets very close to the star, and then our solar system kind of also have two debris belts, like one from the asteroid, one from the comets. And then further out, there are like gas giant and ice giant, right? So the question that really interests me is what happens to the solar system in about 5 billion years when the star becomes a white dwarf? So this is kind of a cartoon illustration. And hopefully by the end of the talk, I'll be able to convince you, hey, there's a lot of things happening around the white dwarfs. And in a way, they somewhat resemble our solar system. There are planets, intact planets, amazingly, around the white dwarfs that are still there. And then somewhat close into the white dwarf, they also have a debris belt made of dust and gas. It's quite different from the solar system's debris belt. So we think this is the dust and the gas, and it's coming from like asteroid, comets, like planetesimals that got perturbed into the tidal radius of the white dwarf and then become tidally disrupted. And the white dwarf actually also have planetesimals orbiting around them. We have detected transit features from those planetesimals, which kind of in the process of disintegrating. And then all these material also get accreted onto the white dwarf, creating a so-called polluted white dwarf, which is also very helpful. I'll talk quite a bit about that too. So anyway, so this is kind of the cartoon image, and I want to have an idea. Yeah, so we'll come back to that. for anyone in the audience who do not know what is a white dwarf, I can just say a little bit about that. So this is kind of, so white dwarf is a very common end stage of stellar evolution. We often quote the word 97% of the stars will become a white dwarf, but Patrick was trying to convince me it's more than 99%. But anyway, it's very high. Like majority of stars will end their life as a white dwarf. So our sun kind of is here right now, and in about 5 billion years, it will be a white dwarf. Most of the actual solar planets detected today are orbiting around stars that will become a white dwarf. So most planets detected today probably will become star food and be engulfed. So we'll talk about that in a little bit too, yeah. So white dwarf are actually very, very common. And as an observer, this is the most famous white dwarf. So this is the Sirius. This is a star you can see at night, a very bright star. And so this is actually a white dwarf. So this is a binary star system, and the Sirius actually have a white dwarf companion. You can't see it with your eye, but it's actually, yeah, to me, I'm like, it's just a nice illustration about how white dwarfs are pretty common, but they are pretty faint. So they are a little bit hard to detect. They can be a little bit hard to detect. And if you look a little bit deeper, most of white dwarfs have a carbon and oxygen-rich core. But when we observe them, we mostly see its outer layer. So it has either a hydrogen-dominated layer or a helium-dominated layer, depending on the exact evolutionary history. Because white dwarfs are very dense, it has very high gravity. So kind of any kind of heavy elements would settle in a very short amount of time. It's a very nice property that we'll come to in a bit too. Okay, so that's kind of everything you need to know about white dwarfs. Any questions before I actually get on my talk? Or maybe you're all on the same page. Okay. Okay, so this is kind of the outline of my talk. So hopefully I'm telling you as an observer, I'm telling you how I'm doing to observe the solar system in 5 billion years. And I will start with, I think a very unique thing about these white dwarf planetary systems are really, we can kind of measure the chemical compositions of those extrasolar planets, which is otherwise very hard to do. Then I will get on the topic about, are there planets, intact planets around the white dwarfs? And then I will tell you something that I am most excited about that's coming online. Water break. All right, so we'll start with chemical composition. I have to start with the exoplanet composition from mass-radius relationship. So this was done quite a while ago, but I think the idea is pretty similar, right? For exoplanet observations, you can measure the planet radius, you can measure the planet mass, and then you can put them on that. And then from theoretical calculations, you can calculate with different composition, what are the expected mass radius relationship. Then you can pin down and says, okay, this planet have a composition look like Earth is here, and Jupiter is there, and that planet has a composition of Mars. So these different curves are different from different compositions. Like this one is like hydrogen and hydrogen helium mixed like envelope, or like an iron, magnesium silicate, and all those things. So there's quite a lot of development on that, but I think it's an intrinsic hard problem to solve from this angle, because observationally you can get mass and radius, while from the model there's so many free parameters, right? Like what is the size of the core, how big is the atmosphere, like all these things. So that's like one way to get to the composition. And I think these days with transmission spectroscopy and the stuff with the James Webb, we can also get to the atmospheric composition, but it's still kind of hard to get to the bulk composition. That's why I will tell you about polluted white dwarfs, which is actually quite a different way to approach this problem. So what is a polluted white dwarf? So these are the white dwarfs are actually accreting from those disintegrated planetesimals. So this kind of, again, a cartoon illustration about how it looks like. So most of them have a carbon and oxygen-rich core, but when you look at the atmosphere, actually in a way, they have these heavy elements kind of raining down on the white dwarfs. So once you get very good data and then you try to also run a very good model, you can figure out the composition of individual measurement elements. So we can measure like calcium, magnesium, silicon, iron to a very high precision. Then we can use that to infer, okay, what is the composition of the material that is falling onto the white dwarf? And actually polluted white dwarfs are really common. So if you do the big enough sensitive spectrograph, you find between 25 to 50% of the white dwarfs are polluted. So this is one study. This is kind of the temperature of the white dwarf. This is number, and the biggest one is kind of the whole sample, and the dark one is kind of the fraction of pollution that's detected. The gray one is maybe because for the hotter white dwarfs, the heavy elements could also come from radiative levitation, not necessarily from accretion. So that's why it's like between 25 to 50%. So this is actually a very, very common phenomenon. And then how do we do that? We need to use high resolution spectroscopy. So this is a spectrum kind of taken from a paper a while back. So we are focusing on the calcium line. So this is wavelength, this is flux. And this is the calcium 3933, calcium K line, which is kind of the strongest optical absorption line we would see. And we're just, so here I'm just showing calcium over hydrogen ratio. And just want to say in solar is minus 5.7. So you see like included white dwarfs, we can easily detect like minus 9.4. So it's like almost like 10,000 times less than the solar abundance. So this is an extremely sensitive method. I think we are really probing, we're really measuring like asteroid type material. Like this is kind of the mass limit we are sensitive to. And we're also very interested in kind of the volatile elements, right? Like carbon, like oxygen, sulfur. For those, we need a UV spectroscopy. So this is data taken with the Hubble Space Telescope. And so you see here, I know there's only one line, but there's this nitrogen line. So that was the first white dwarf with actually nitrogen detection. Yeah. Just again, give you some ideas about polluted white dwarfing numbers. We'll be all working very, very hard. We have found roughly about 1,000 polluted white dwarfs in total. So numbers increasing. And then in terms of two elements, if we want to do something, right, figure out the composition, it's about 300. And the four elements, there's about 30. And I think most of them are actually modeled by Patrick Defoe and the group here. So their model is very essential to this kind of polluted white dwarf work. So we've been working hard, but I think the sample size is still pretty small. And I think in order for us to say something about the population, we really need a larger sample to tackle this problem. And then, yeah, I was saying just we are kind of moving away from the astronomer's periodic table to this, like, and for that's why we really try hard to avoid using the word metals, because metal in geochemistry means something else, right? We try to say heavy elements, but again, it's not that heavy. We mean anything with an atomic number more than 2, right? But anyway, so back here, these are all different elements, heavy elements that have been detected in polluted white dwarfs. So it's actually quite a lot. So 24 different heavy elements have been detected in polluted white dwarfs. And I highlighted these 3 is because they were only detected in the past few years. So I thought like it's quite a nice list. If we're thinking like, hey, we are probing this kind of planetary composition with all these kind of elements. So I've told you the story. So what have we seen really? How do they look like? So this is the extra planet. So this is a mass fraction of like about, here it's about 20 or so white dwarfs, polluted white dwarfs, where we have all these detailed measurements. So I'm showing like Earth and the comet Halley here in comparison. And here I'm plotting kind of the mass fractions, right? So these are like different number of white dwarfs. So I think maybe from the first look, you say like everything look like first order pretty similar to bulk Earth, right? Like they are dominated by oxygen, magnesium, silicon, and iron. We haven't really found anything too exotic. But if you look a little bit further, like the object here, they seem to have a lot of oxygen. Like actually for some system, they have so much oxygen that there is not enough other elements to combine to like form like the oxidide. So in this case, we think it's very possible water like is also an important constituent in these systems. And then on the other side, you also see like the few systems have quite a lot of iron. So they seem to be like a mercury analog. So maybe they have a very iron-rich core. And I was actually recently talking to a geologist. They actually want to take the composition measured from the white dwarfs to do some lab melting experiment to see like what would happen actually if like given the real planet formation scenario, given these kind of abundance, what kind of minerals would be formed. So I think that would be super neat. Yeah. They say like we're taking realistic planet composition to do this work because currently, like I guess in Earth science, we all take like the Earth composition, right, as a starting point. So you see like there is a range. And then here we focus a bit more on the volatile elements. So this is, and this one is actually a logarithmic ratio. So it's sulfur over calcium and carbon over calcium. And then I'm plotting like the nearby FGK stars are high up there. So you see like a stellar composition is actually quite enriched in the volatiles like carbon and sulfur, right? And then here are the chondrites and here are the different meteorites, and these are the polluted white dwarfs. So you see like the material accreted on the polluted white dwarfs, they all appear to be pretty volatile depleted. I mean, you see this one guy up here, right? It's like almost like solar, but we only find one. Like almost all the other objects, they are pretty volatile depleted, kind of just like the meteorites in the solar system. So everything seems somewhat consistent. And then you can also look at a larger sample if you really want to say something about like the overall, the property of the overall population. So in this study, we were investigating like a differentiation. So basically, we know Earth is differentiated. Earth is not just a huge blob of material. Earth have an iron-rich core, like magnesium, calcium-rich mantle, and a silicon-rich crust. So what this work trying to do is, I think they took 150 polluted white dwarfs that with both calcium and iron measurement, and try to plot the cumulative distribution, which would show as the magenta line. And then say if you just take the star composition, and which is like show as this dashed line, like these two distribution really don't agree. Like so, if you just take the star composition, you wouldn't be able to match kind of this wide range observed in polluted white dwarfs. So what they find is actually you need both differentiation and some additional heating. So which is this red dashed line. Like so, in order to measure the like range that we see in polluted white dwarfs. So from that, it seemed to see like on a larger scale, you can say like these exoplanetesimals seem to be differentiated. That's how we explain this range of calcium to iron ratio. Okay, so something about polluted white dwarfs. That's a summary of the very first part of the talk. Hopefully, and I've convinced you that polluted white dwarfs directly probe the chemical compositions of those extrasolar planetesimals. And then so far, we've seen oxygen, magnesium, silicon, and iron are in very familiar proportions in those extrasolar planetesimals. Are there any questions before I move on to the next part?
This one. The histogram you showed where the fraction is 25 to 50%. There seems to be very few stars in this. The original sample, what was it? Was there any bias in that sample?
Okay, yes. So let me just go back. Sure. I think you're asking about this, right?
Yeah.
So you're asking about this sample selection. So this is actually from an HST cost study. So I guess maybe the bias is these are hot white dwarfs, right? These are hot DA white dwarfs. But there is kind of a different study focused on cooler white dwarfs, say between 10,000 and 15,000, and the fraction is the same. It's about 25 to 30%. So. Okay,
and your 1,000 stars that show at least one, that's from what kind of sample?
Oh, the 1,000 is from Montreal white dwarf database. Okay. So that is not a homogeneous sample. But yeah, so I would say, I think this fraction, this large range, I would say it is about 25, 30%, because we do have another paper which is going to come very soon is from the DEDI sample, and it's focused on much cooler white dwarfs. And we find it's still like about 30%, which to me is quite amazing because whatever the mechanism we think is to bring in the asteroid, it seemed to be very efficient and they seem to be keep going for quite some time. And even for those cool white dwarf, like 10 gig years old, the pollution fraction seemed to be just the same. Yeah. I don't know, for dynamic theorists in the group. Yeah. Thank you. Yeah. Any other questions if I move on? Okay, maybe you're all convinced. Okay, I'll go down to this. All right, so yeah, so this is all I would say about polluted white dwarfs, but there's a lot more. If you have any other questions, ask Patrick. He knows everything.
I want on the second button. So this means that the refractory elements have very familiar valence ratio in both white dwarf planetesimals. And so we think it's reasonable to assume that planets are formed with the same abundance as their snow.
Yes, for the refractory element, definitely not a volatile element, but for the refractory elements, I think that's actually one thing is like how good do we trust the error bars, right? That's the thing I talk a lot to Patrick about too, because if you look at this, right, there are some ranges, right? Like, but for example, like for this object, if you say the uncertainty in iron is 0.3 deg, then maybe it's all consistent. But if you think like we really trust our error bars, if it's like 0.1 deg or even less, then maybe we can actually say a bit more about that. So I think it's a little bit case by case. familiar proportions means 2 zeros order. We don't find anything, like we haven't found any carbide planet for sure. We haven't found anything like completely like out of
the reason I'm asking is that this is quite fundamental because, as you know, you can't constrain the internal structure of the planet with only the mass and the radius.
Yes,
But
exactly.
if you can assume that there's still the abundance of the planets the same as the whole, which can measure,
Yes,
then that's becoming
Yeah.
quite useful.
yes, that's it. So I don't know, Patrick, what do you think?
Well, we don't know the abundance of those because it's there.
No, no, but
No, I know. Yeah, but at least
Yeah,
the range that you get is similar to what we have in the solar system.
Yeah.
Which is already a good sign.
okay.
And I think it makes sense from the
Well, the
planet
last
formation
formation of the same perspective.
Maybe a nice question, but where's the carbon?
Exactly, good question. But it's the same in the solar system. So actually in the solar system, people also ask about the question, what the carbon? Because we used to ask, it's very well known, I guess, for geologists, but for astronomers, if you ask them what is Earth made of, a lot of time we would think carbon because it's so common everywhere, right? But Earth is actually very much depleted in carbon compared to the sun. So I think one idea is just the carbon is a volatile element, right? It condenses much further away. So like a comet, like Comet Halley has quite a lot of carbon, but like the inner solar system is actually quite depleted in carbon. So I think the idea is just the carbon condensed much further out, but not in the inner solar system. But there are actually people actually work on kind of the overall carbon budget of the solar system. Be like, does everything work out? And maybe somehow we just don't have, like if you calculate the whole mass of carbon in the solar system, it actually maybe not enough. That actually people are working on that. Yeah.
We have a question from Derek online. So is the assumption that all atoms sink below the atmosphere in similar timescales? Or if not, will it not change the differentiated core result?
Yes, that's a very good question. So I think the question is the settling time of different elements. Definitely, like different elements do settle a little bit differently. And so in a way, we do need, in order to make this kind of plot, we do need to kind of know the accretion state, right? So typically we classify them into kind of the build-up stage, which means accretion just happened. What you see is what you see is what it is, or maybe a steady state, which is kind of corrected by like the settling time. But the settling time between different elements typically is within, a factor of 2. So it's not the biggest uncertainty. But if the accretion is in more like decaying phase, which means accretion has stopped, but the element have not fully settled, that phase can be a little bit tricky. So for example, like I guess here, if you only see, because iron is pretty heavy, right? Well, actually, it sinks pretty fast, so it's the other way around. So if you see something very iron depleted, then you might wonder, is it because it's in like the decaying phase? But we have some other indicators, like most of the system here, actually, they all have a debris disk around it. There's dust, there's gas, so we are pretty certain the accretion is ongoing. So yes, there are different levels of uncertainties in kind of making this plot, for sure, yeah. Oh, any other questions? I'm glad getting good feedback. Okay, assume you are all in buying to this. I'll move on to the second part, which is something we are more recently working on, is a new circumstellar gas disk model. So again, going back to this picture, I've talked about kind of the polluted white dwarf part, which I think is a very successful method. And we've been working very hard trying to get the composition of the planetesimal. But there's also the stuff around it, right? There's also the dust and the gas. So presumably they all come out of the same material. Then we should be able to constrain the composition from the dust and the gas. Then we can compare and contrast with the polluted atmosphere. And maybe that will give us some insight, either from the tidal disruption process or like the white dwarf modeling process. So again, the periodic table. And then the one highlighted in red is the species we have detected also in circumstellar gas. Most of them is actually detected on one system, WD1145, which Erica is working very hard on right now. And then for some of the other systems, it's really, I think this is really only become possible in the past few years when we have a lot more systems with gas line detection, a lot of different species. And that's why I thought this could be a really kind of new promising method to get the composition of the circumstellar material. So maybe I'll first talk a little bit about 1145, which is kind of the first white dwarf which have this broad circumstellar absorption. So I'm a spectroscopist, so I do a lot of spectrum observations. So this is zoomed in each kind of part. It's like iron, calcium, chromium. And the x-axis is velocity, and the y-axis is normalized flux. And the black line is our data, and the red line is Patrick's model, kind of trying to fit the white dwarf photosphere. And I remember when I first got this data, just the lines look weird, right? And the magenta is basically the data minus the photospheric model. And I remember when I first got the data, I saw that I did something wrong in my data reduction. Like I've never seen this kind of broad thing there before. I saw that I tried very hard to get rid of the feature, but I just cannot get rid of that. Then I'm like, okay, maybe it must be something real. And then I realized, oh, it's almost present in every single, most of the circumstellar absorption line. Then we realized, okay, maybe we're actually seeing some kind of circumstellar disk, absorption from the gas around it. However, the disk should not be in a circular orbit, because if it's in a circular orbit, right, because you're only seeing this part, it must be symmetric, like from plus 50 to minus 50 kilometers per second. What we are seeing is something very asymmetric, like here from maybe like, I don't know, minus 100 to plus 200 kilometers per second. So the configuration is much more like this. So we are kind of seeing an eccentric disk, and we are only seeing absorption from this part, right? Like absorbing. That's why we are seeing such an eccentric additional absorption and a very eccentric, like around the white dwarf. And then indeed, Patrick's previous master student mode come up with a eccentric ring model, kind of trying to model the composition. So this is like, well, this is first the geometry actually, trying to figure out, okay, we need multiple rings and where the ring is. And this is the model. I thought, so similarly, again, the black line is the data. The gray line is the white dwarf photosphere model, and the red line is by incorporating this additional absorption from the circumstellar gas. And actually works really well. And we got much more data on this, and Erica is working very hard, kind of trying to figure out what is the circumstellar composition and compare with the photospheric composition. Because up to now, 1145 is still the system with the most circumstellar absorption detected. But the complicated thing here, as you can imagine, it's an eccentric ring, right? And it's actually precession. It actually will precess under general relativity. So the line strength kind of changes. And so kind of each epoch, you need to get the right configuration. Then you can back out the composition. So work in progress. Yeah, then I will tell you a different system, which is a little bit easier. That's a paper we just submitted. It's about this white dwarf, which actually shows emission. So previously, we were talking about absorption. And we now know maybe about 20 systems that show circumstellar emission, also from circumstellar gas. So in my mind, it's probably just a geometry effect. For 1145, it's much closer to adjunct, so we are only seeing the absorption part. But for this, it's just it's not completely adjunct. So we see kind of these, not very nice, but anyway, so we can see these kind of emission features. So this is a complete view of this white dwarf. Again, like a wavelength, flux, and we'll zoom in to see the emission feature. So this is a much easier system to model compared to 1145. So again, so this is the velocity, and this is the normalized flux. And you see the line is very, very symmetric, right? So they have this double peaked feature, which is indicative of an orbiting like gas ring around it. And it's stable, which is very good. We've observed quite a few times throughout the years, nothing changes. So which means we just need to focus on getting out the composition, which is I'm really interested in. So we use a photo annihilation called CALDI to help us. So we think a white dwarf is the only heat source in the system, and the configuration here is much easier, right? So we're just doing like different rings. Yeah. And so here, I'll just show you some example fits. So again, so this is the velocity, and this is normalized flux. The black line is the observed spectrum, and the orange color is the model. So this is the calcium 8500, which it's not perfect, but I thought it's okay. And this magnesium line is actually a blob of two lines, so we didn't quite resolve. I mean, yeah, I think they're just too close together. It cannot really be resolved. So we got the calcium, sodium, oxygen, and the silicon. So we can kind of all putting them up together. And so this is the composition. This is how it, so yes, it's a little bit hidden. So anyway, so this is oxygen and sodium, magnesium. What's the other one? I think it's no, I think it's calcium. So I'm plotting over silicon. So the red cross is the photospheric value, the blue dots is the circumstellar gas value. And then I also put Earth there as a comparison. So at least for this system, it seemed to be consistent. Like within the uncertainties, we didn't really see any big difference between the circumstellar gas composition and the photospheric composition. But the circumstellar gas composition is have pretty big error bars though. And you may say maybe oxygen is slightly enhanced, but it's really all consistent within the error bars. But I think actually it's quite promising because we have maybe, a dozen of systems have multiple gas species detected. So we can really try to compare the gas composition with the photospheric composition. Which brings me the summary of my second point. Hopefully I've convinced you it'll be cool to model the gas composition to figure out like what's exactly happening with the gas. And I think there's quite some opening questions in this general work, use white dwarf to get to the composition, is what is the property of the population? I feel like we've done a few objects here and there, but it would be really nice to know what is the overall property? Like, do we see any trend with the white dwarf mass? Do we see any trend with the cooling age of the system? And also really, I think we really need to understand the systematics. Like, are we really saying something to 0.3 DAC or 0.1 DAC? And I think the geologists doing the experiment really depended on that. If we think everything is really consistent with solar, then maybe the Earth's composition is really just fine. Okay, so that's the end of my composition part. Any questions before I move on and talk about planet?
Yeah, is there a correlation between the presence of the disk and the amount of metals you see on the white dwarf?
Right, so okay. Sorry. In this talk, I guess I didn't talk much about the dust disks. Yes, so some white dwarfs also have dust disks, debris disks. We think they are about maybe 2 to 4%. So the occurrence rate of disk is actually much lower than the occurrence rate of metals, right? But we do find the most heavily polluted white dwarfs often have disks. So there is a correlation if a white dwarf more heavily polluted. And depending on how you define heavily, but I think we define it as like the mass accretion rate. So if you look at the white dwarf that is accreting, like have a very high mass accretion rate, then it's very likely to have disk. But there's another, there's always something but, it seemed to be rare to find the disks around cooler white dwarfs, say white dwarf cooler than 10,000 Kelvin. But I think the idea there is maybe those disks are just too cool. We just haven't found them yet. Maybe James Webb will help us find some cool disks because previously it's all done with Spitzer, basically.
And you have white dwarfs that have the disk, but nothing accreted on the white dwarf?
I don't think so, no. Yeah. So, I mean, there's a few cases which the white dwarf have infrared excess. I feel like I'm not 100% convinced the infrared excess come from a disk. It could come from a companion. So in that, there's a few cases, then we don't see pollution, but almost all the white dwarf with the disk would always show pollution, which is also very good, right? It kind of makes the picture together. Yeah. Sure.
In the examples that you showed, are we looking at the disk edge on, or are these tilted?
Yeah, exactly. So I think in the case of 1145, where we see broad absorptions, I think the disk is very likely to be edge on, right? That's why we see the absorption. But I think in the other system where we see the emissions, I don't think the disk is edge on. Yeah. Agree? Yeah.
Well, so regarding the tidal disruption, is it given that this process will destroy everything? Like, what I mean is that let's suppose you have a fairly big planet with an iron core. Could you imagine that only the mantle will be stripped and you would leave the iron core, in which case your runoff current will be biased to profit driven?
Exactly. So that's a very good question. So the question is just that if you have a differentiated asteroid going to do the tidal disruption, right, then maybe the mantle or crust will disrupt first. And then the iron core might take much longer or might be much closer into the white dwarf to be disintegrated, right? Then you might see a difference. And that's exactly what I'm hoping to go with this circumstellar gas. So maybe like the crust and the mantle had already been accreted onto the white dwarf, but like the iron core is still in the disk or the iron core is not there yet. So I think that's really what we are hoping to go with it. So if we find any difference between the composition of circumstellar gas and the photosphere, I think it could indicate that. Yeah. Yeah. So stay tuned. Other questions? Okay, I guess people all want to hear about the planet, right? All right, yes. So second part of my talk, are there planets around white dwarfs? I feel like I got asked this question really a lot whenever I give a talk before about polluted white dwarfs. They always ask, have you guys found a planet yet? Now I can say yes, there are actually a few. and I'll be happy to share with you. So first is, I just want to highlight that we have really used a very diverse method to detect planets around white dwarfs. So here I'm showing an orbital separation. So it's, it's pretty large scale in AU. And this is a planet mass. We have 4 dots up there. I think there are about 4 systems. So this one, I will go by chronological order. Yeah. So this one found actually pretty early on in 2011. And that was doing by a Spitzer survey. So it's a direct imaging survey. Well, they were searching for brown dwarfs, right? And then at the time, actually, that's kind of called the coolest brown dwarf. Even now, maybe you can still argue if it's a planet or it's a brown dwarf, because it's like 2,500 AU away from the white dwarf. They are just moving together as a common proper motion pair. And I think the big question there is, does that planet kind of, how did that object form, right? Did it form kind of like a star, like the white dwarf and the planet maybe formed just like a star, or like maybe it was captured later on, it was like more like, then maybe it's more like a planet. And then in 2019, there was also this evaporating Neptune-like planet detected around the white dwarf. So this is like very, very close in, like the mass, I think, is Neptune size. I think for that specific system, what they seem is actually a volatile rich disk. It's like a carbon and sulfur rich disk around the white dwarf. And the system do not have infrared access. And after they rule out all kinds of scenario, they say, okay, the most likely case is probably the Neptune-sized planet in the process of evaporating around the white dwarf. So that's why it's a little bit disintegrating, yes. And then there's also this system, which is discovered by microlensing. So basically, they were just looking at galactic bulge, looking for microlensing event, and then they find an interesting signature, and the team tried to follow it up, and they find that they could not detect the host star, even with like a CAC AO, and that's how they say, okay, the star must be a white dwarf. So like in a way, so it's like a 2 Jupiter-sized planets, like a few AU away from the white dwarf. So in a way, this is a planet fits more into my planet around the white dwarf cartoon picture. I kind of expect that's where they are. But it's a little bit hard because it's a one-off event. You can't even see the white dwarf. We can't do any further characterization on the system. But that's just a general property of microlensing, right? And then what I want to tell you more in this talk is about this system. It's actually discovered by TESS, and it's a transiting planetary-sized object around the white dwarf. The mass, at least up to now, is still not super well constrained. I'll tell you a bit more why, but I think it probably will come down a little bit, maybe more like here. So this is a system, this is a transiting system detected from TESS. So this is the top of the TESS light curve, which shows like a very deep transit. And also it's symmetric and it's not changing, unlike some other disintegrating bodies, which we find the light curve keeps changing. This one looks very stable. We followed up with different optical and infrared and the Spitzer, like all looks very stable. So which is very, very good, right? And then very different from normal transit observations. Here, the transit depth is 56% because the white dwarf is tiny, right? So like the planet is actually bigger than the white dwarf. EV, but the transit duration is only 8 minutes. So that's hard. Yeah. The period is 1.4 days. And from that, we know it's a Jupiter-sized planet. We can work out the semi-major axis is about 0.02 AU. And the equilibrium temperature is only 163 Kelvin. So it's among the coldest transiting exoplanet ever detected. Only a little bit hotter than our own Jupiter, actually. Anyway, so once we saw this information, we're like, okay, we really need to follow up, right? And then first thing to do, we're like, okay, let's really characterize this white dwarf very well. Let's see how much we can say about the white dwarf. So we got it from optical all the way into the infrared. And then we find it's a pretty faint object, almost 17th. And unfortunately, it's a DC white dwarf, which means there's no spectral lines. So like, so this is a pretty like a featureless spectrum, right? Just look like a black body. And the white dwarf is actually pretty cold, like 4,500 Kelvin, even cooler than our sun. It's a pretty old white dwarf. I think the total age is almost like 10 gig years. And another interesting thing is it's actually in a triple star system. So this is where the white dwarf is, and it has an M dwarf pair. Oh, it actually have an M dwarf pair next to it. So which also make it dynamically really interesting. And then we were thinking, okay, what is the mass? because from the transit light curve, we know it's a Jupiter-sized object, but it could be an M dwarf, it could be a brown dwarf, it could be a planet. How do we do it? I mean, typically people would go do radial velocity, but this is a DC, so there are no spectral lines, so it seems pretty hopeless. So what we did is we actually tried to do it from the light curve. So we are comparing, so this is the optical light curve, and this is the Spitzer light curve at 4.5 micron. So we were hoping to directly detect thermal emission from the planet. Then coupled with some planet models, we'll be able to put a constraint on the mass. But in this case, you see like the Spitzer light curve and the optical light curve looks very comparable, right? The depth, shape, everything's the same. So it means like even at the Spitzer wavelength, we did not really detect any emission directly from the planet. And with that, and with some model and the system age, we can constrain the mass to be less than 13.8 Jupiter mass. That's why like it's kind of a big range. It could be less, but that's the best estimate we have right now. Well, we had back then. Yeah. Okay, then since we know that system, we're like, okay, let's try to learn more about the planet. So we got some time to do transmission spectroscopy. Since I'm at Gemini, I'm like, okay, let's try to use Gemini and to see what we can do about this system. So we use Gemini GMOS, and we covered this optical wavelength range. It's actually very challenging to observe in terms of transmission spectroscopy because the star is very faint. The transit duration is only 8 minutes. So we actually have to get 10 transits in total to build up enough signal to noise ratio to say something. This is just, this is data. So we indeed got 10 epochs. I feel very proud. I did my timing calculation correct. We did get a transit every single time, right? And then you see like, so each one is just each data point. So you see like every transit, we really only get like 6 data points. We have to like build them together in order to analyze the light curve. So this is putting everything together. So the top, yeah, so this is the actual light curve, and the black line is the fit, and there it's a residual. So the top gray one is like the white light curve, and then I break them up into different color beams. And then, so all this is pretty standard, but as we work one step further, we realize, how do we analyze the light curve? Because typically, again, for exoplanet studies, the transit depths would equal to kind of the ratio of the planet radius to the star radius squared, right? But in this case, the planet is larger than the star, and it's a grading, it's a grading of it, right? So we have a cartoon to show you. So this is the planet, this is the white dwarf, and then on the right-hand side is our model spectrum, right? So you see, like, depending on when you observe, I'm gonna show again. Depending on when you observe, the overall transit depth is different, and we were hoping to see these little features, right? And the strength of those little features also different, right? So we actually have to develop, not me, but one of our team members developed a kind of a new framework. So it's a little bit mouthful, but it's called lane darkening corrected time average transit spectra. So we have to use that term rather than like the traditional planet to star ratio, kind of to analyze this transmission spectrum. So yeah, so after all this, what did we get? So this is what we got. So this is the wavelength, and this is the average transit depth. The green dots are our transmission spectrum, and then the red line are different models. I think for me, it's the hardest I've ever worked to prove it's a straight line. So in the end, basically, we're just saying the green dots are pretty similar to a flat line, but apparently it's very common in this transmission spectroscopy work. So this is just assume there's a no cloud, we can put a limit on the planet mass based on the non-detection of any spectrum features. And then if there are the clouds, the planet could be even less massive. So we tried, but I don't think the result is super exciting. Basically, we didn't really see any optical features. And we think the planet could still be anywhere from 0.7 Jupiter mass to 13.8 Jupiter mass. But the good news is we actually got JWST data on this system with different mode. So yeah, so data analysis is on the way. I think the result looks pretty interesting, and hope you'll see the paper soon. Yeah. Okay, with that, actually that is the end of the second part, or third part. So hopefully I've convinced you we've used very diverse methods to detect planets around white dwarfs. And to me, I'm still curious to see what is the most promising method to finding more planets around white dwarfs. And really, there's so many open questions. Maybe one of them is, can we say something about the population of planets around white dwarfs and how different or similar they are compared to main sequence stars? Maybe I'll make pause here to see if there's any questions. Sure.
I believe Fontaine discovered a planet, right? Using astroseismology, no?
Yes.
Yeah,
Yes,
but
it was a dwarf.
Yeah, but what?
But around the sub-dwarf.
Sub-dwarf.
Okay.
Sub-dwarf. Sorry.
All the same.
Yeah, I mean, in general, I feel in the literature for white dwarfs, people also talk about astroseismology to detect them, but it seems I'm not sure if any of them are really confirmed. Like some of them, like, oh, they have this signature, maybe it is, but then when you keep observing a little bit longer, oh no, like it's just something on the white dwarf that we don't quite understand. Yeah, and actually, just about a year ago, there is this Gaia astrometry planet, which we thought that would be really cool. But then in the end, it's a software bug. So, but I think the Gaia would still be quite like with astrometry. I think it could also be really interesting. Yeah. Will be sensitive to the parameter space, very complementary. Yeah. Any other questions?
Very curious about the GWST observation. Was that transmission spectroscopy or just straight the spectroscopy object?
Yeah. So actually it's two programs. One is transmission spectroscopy. The other is also trying to detect the thermal emission, kind of repeat the Spitzer observation, but with James Webb. And I think, I mean, there are definitely wiggles, right? So, but I think it's just hard to see like what is real, what is not. So I think that's what I'm not the person working on that, but our team member is working on that.
I don't know if it's helpful, but have you looked at the like reverse transit as well, on the other side?
On the other side, yes, the secondary eclipse, right? I think they've observed. Actually, I'm not quite sure. I thought we did, and I don't think we see any signature. Yeah, too. Yeah, the secondary transit, right? Yeah.
Yeah, no, just the planet's bigger than the white dwarf, and maybe like that's also a useful way to look at it, but I don't really know about it.
Yeah. Okay.
You can't even detect the thermal signature of the planet.
You see a reflected one.
Yeah, I don't think we see. Yeah, I don't think we see anything. Yeah, definitely not in the optical. But I think in the infrared, I think in the infrared we only done the Spitzer, and I'm pretty sure we are focused around the like primary, trying to detect the thermal emission. Yeah. Yeah. Okay, with that, maybe I will just go forward and tell you what I'm more excited about coming up. Yeah, so looking forward, just it's a biased view, is what I'm personally more interested about coming up in the field. We already mentioned a few times JWST, yay. I think we are all, yes, proposal is due in 3 weeks. So we are all working very hard on writing JWST proposals. So one aspect I talked to a little bit earlier, me personally very interested in, is to get the mineral composition of the dust disk. So this is work done by Spitzer Space Telescope, but this is actually from a reprocessing. I mean, Spitzer is 20 years ago, right? But the white dwarf, I think the hardest thing with white dwarfs is they are all just very, very faint. So this is actually done with the reprocessing, like better sky subtraction, better calibration. And this is focused around the 10 micron feature. So the blue dots are the data. So you see like they all have like very different. So 10 micron is like a huge like a dust feature. But if you look into them, like the shape all looks very different, and they all have different kind of peaky features, and you can try to match with different mineral features. So JWST will return much better, like much better quality data. So I'm actually hopeful maybe like soon we'll be able really to tell you what is the mineralogy of those debris disks. And then we can compare from the dust composition to the gas composition to the polluted atmosphere. So I think that part will be super exciting. We get some time and I hope we will have more objects observed. So I think that's something that's definitely coming. And another thing we talked about is about finding planets, right, with JWST. So this is a simulation. So this is a wavelength, this is flux. This is comparing like a white dwarf with like an Earth and Jupiter model. So what you can see, because white dwarfs are really kind of small and faint. So like for Jupiter, I guess beyond the 30 micron, Jupiter is actually brighter than a white dwarf. So like infrared is really the way to go. I mean, James Webb doesn't go beyond the 30 micron. Maybe we need a far infrared emission. But anyway, the sensitivity is definitely there. And so this is what you look at as an infrared axis. So again, like the top is a Jupiter axis, and the bottom is like an Earth-sized planet. So just say at a 17 micron, the contrast between Earth and a white dwarf is 0.01. Just in comparison, between Earth and the Sun, it's 10 to the minus 6. So actually, just the past JWST proposal, there was like 2 programs approved just to trying to direct image those planets around white dwarfs. I know there are some people here working on that too. So I think that would be like another method. I think that would be pretty promising. Just trying to directly see the planets around white dwarfs. Yeah, and another thing I'm quite excited about is DESI, which is a dark energy spectroscopic instrument. It's actually have surveyed about 50,000 white dwarfs. It's like the largest spectroscopic survey of white dwarfs. I think it has seen more than Sloan. And so this is kind of an HR diagram. And we have found almost 1,000 polluted white dwarfs. Most of them are new. So this is the Gaia GP minus RP, and this is G. And these are like all the interesting white dwarf kind of highlighted there. So definitely like another, at least increased by the non-polluted white dwarf by about a factor of 2. So yeah, we have lots of data to work on. And then there's also LSST, right? I think which is supposed to come online later next year. So again, in terms of detecting planets, this is one study that's done a few years ago. Basically, because LSST will go so deep, it will observe about like 10 million white dwarfs. So we'll go much, much deeper. And then, and again, white dwarf is so small, like you are very sensitive to like even smaller mass object. So if every white dwarf do have a planet, we will have like 10,000 detections. And if at the end of the survey, we don't find any planet around white dwarfs, it means the occurrence rate is actually really, really low. So I think that's something we'll be really need to do as well. And then as we talk about Gaia is still ongoing astrometry. Test is also still ongoing. So there may be more transiting objects there, like waiting to be discovered. Last but not least, since I work at Gemini, I have to bring you back here. So Canada is a partner of Gemini Observatory, and we have a whole suite of instruments that you can propose for. And Canadian time is really not that oversubscribed. So if you are interested in using Gemini or using any of the instruments, please let me know. I'm the instrument scientist for Maroon X, which is a high precision radio velocity spectrograph. And we also have GHOST, another high resolution spectrograph that just got commissioned. And IGRANS 2 is an infrared spectrograph that actually is being commissioned right now. So yeah, so I'll be happy to talk to you more about that as well. And with that, I just want to say thank you for your time and happy to take any other questions.
Thank you for taking the time. So we still have a few minutes before the other class come in. So if you have more questions, now is the time. Or you already, ask your question during the talk.
Oh, cool.
You mentioned the astronomer periodic table and highlighted a few elements. Is there any hope of expanding that one, or is that all we can see?
I don't know what
And for context, because in exoplanet like ultra hot, we see like almost exactly the same elements.
Yeah.
But there's a few differences.
Okay. Okay, I think maybe it would be nice to compare and contrast. It would be good to know what have you guys detected in the atmosphere, right? Yeah. I think I know. Well, okay. I think in a way this is even a little bit deceiving to show it like that, because this is detected in all polluted white dwarf, right? For a single one, I think the maximum we have the really not a single white dwarf, we have detected all these elements. So I think it will be tough.
When I wrote my code, my first code, I include all the element up to copper because I didn't think we would see anything else. I would have to modify my code to something else.
So you can't do like SR.
That's how I can
strong
right now.
yeah.
It's been found in one star.
But we're in exoplanets, we're now seeing one under that, the like barium.
Oh, okay.
Like atomic number.
Yeah.
64 or something.
Yeah.
So maybe you could find that in white dwarf too.
I think what a proper way to do it would be we put in like the Earth, starting with the Earth composition, ask Patrick to do the model, make a prediction, what are the strongest lines and what is the expected. I think we try to do that, but I think it will be difficult with the current high resolution spectrograph. I think we really need a 30-meter spectrograph.
And we didn't see any other big stars, and the GD 362, which is the most probably the white dwarf, so and probably the abundance are so low that we don't expect one, or there is no transition in the optical.
Yeah.
So
Yeah.
Maybe there's something hidden in noise that we've missed, but it would be very frank in those things.
Yeah, I think we may need a larger telescope and a higher sensitivity to detect them. Yeah, but
Question from online. Has anyone calculated if Doppler beaming induced by the planet is strong enough to be detected from the Vanderbilt planet?
wait, what is strong enough?
If the Doppler beam induced by the planet is strong enough to be detected for the Vanderbilt planet.
Yes, I think we are working on paper, or we just finished the paper, and I don't think we can detect that. Yeah, thank you. Yes, yes, good question. Yes, we can really detect the Doppler beaming effect. Yeah, we can put a constraint. Yeah. Yeah.
C'est vraiment question, on va remercier.
Thank you. Thank you.